In this lesson, we're going to define general pyramids and cones. And a general cone is defined as a solid figure with a curved or semi-curved base. And a general cone has a vertex. So what makes it a cone is the fact that it has a base and all the sides lead up to a single point, which is the vertex. A pyramid has a polygon base. So a pyramid, if you think of the Egyptian pyramids, that's the most famous one, they have bases that I believe are squares. So any cone that has a base of just line segments is going to be considered a pyramid. But again, the sides meet at a single point, which distinguishes cones from cylinders. So we're going to further define general cones to some more specific definitions. A general cone with a disc or a circle as its base is a circular cone. And then a general cone whose vertex lies on the perpendicular line to the base that passes through the center of the base is a right circular cone or a right pyramid, depending on the shape of the base. So when you think about cones, ice cream cones or whatever, those generally have the vertex centered over the base. So whatever the base is, everything would be centered over it, and it's not leaning to the side. But what you need to understand is that a cone doesn't have to have its base centered over, or it doesn't have to have its vertex centered over a base. So we could have an edge over here, and this would still be a cone. If I cannot draw a cone very well, but if all these lines that are connecting that form the sides come back to a vertex, it's still a cone, or it's still a pyramid if the base is a polygon. Now we're going to talk about cross sections again, and a cross section of a figure is a slice that's taken parallel to the bases of the solid. So a cross section is supposed to be specific, but what I've shown you in the Regents exam is that sometimes cross sections are confused with slices. A cross section is supposed to be parallel to the base because we have other theorems that rely on cross sections. A slice would be any other slice through this that's not parallel to the base. But when you have cross sections, the shapes of the cross sections will always be similar to the base of the cone. That's because we're slicing parallel to the base, and the cone actually, the vertex of the cone acts as a center of dilation, where we know that images are going to be similar to each other. Alright, so we know that when we have similar images, the scale factor is the ratio of corresponding lengths. It could be the distance from the vertex, or it could be corresponding sides within the images themselves, but the scale factor is going to be R. And then we know that we can take the ratio of areas just like before. If I have a cross section in a cone, the ratio of areas is going to be equal to the scale factor squared. So if I have two areas, if I have area B and area B prime, that ratio is going to be equal to the corresponding scale factor squared. So here's what we can do. We have a triangular pyramid, and a plane is cutting through the pyramid, so it's parallel to the base, and it results in the cross section A prime, B prime, C prime. The area of ABC is 25 square millimeters, and I want the area of the smaller cross section. Well, we're going to find the scale factor first, and we're going to look at the sides. Again, the vertex acts as the center of dilation, so the distance to A from the vertex and the distance to A prime is going to set up our scale factor. Now, we want to go, as I always said, when we do a scale factor, it's image over pre-image, because we have the area of the pre-image and we want to find the area of the image. So this scale factor is the ratio of the corresponding sides, and it's going to be 3 over 5. That means the scale factors of the area is going to be 3 over 5 squared. So the ratio of the areas, if I'm going from pre-image to image, is 3 over 5 squared, which results in 9 over 25. So if I want to find the area of the smaller triangle, I can just multiply the area of the large triangle by the scale factor for the area. So it ends up being the area of triangle A prime, B prime, C prime is going to be equal to the area of triangle ABC, which is 25, multiplied by 9 over 25. So this area ends up being 9 square millimeters. It's an easy way to find areas. That looks like a Q. An easy way to find areas in a problem when you have corresponding distances and you know the area of the base. So the next example demonstrates that we don't need edge lengths. We can use any pair of corresponding lengths in the pyramid or in a cone. So in the following triangular pyramid, a plane passes through so that it creates a cross section, again, of A prime, B prime, C prime. This time we have altitudes. And the altitude from X to V of the entire pyramid is 18, and the altitude from X prime to V is 12. So we can use these values to set up the scale factor, the linear scale factor. Now, this time I have the area of A prime, B prime, C prime, and I want the area of the larger triangle. So the scale factor I'm going to use, if I'm going to multiply it by the small area, is going to be 18 over 12. And again, I'm writing it this way because I want the area of the larger triangle. So 18 over 12 reduces to 3/2. That means the ratio of the areas is going to be the square of that. The ratio of the areas is going to be 3 over 2 squared, which is 9 over 4. That's big area over little area. So the area of ABC is going to be the area of the smaller triangle, which is 28, multiplied by 9 over 4. That ends up being 63 millimeters squared. So you don't have to set up a proportion if you can understand that if I want, I usually say the scale factor is the image over the pre-image, but in this case I have the area of the image and I want to make it larger. So that means my scale factor has to be greater than 1 instead of less than 1. And then I multiply it by the smaller area, and that gets me the area of the larger triangle. And again, it's important you find the scale factor and you square it to get the scale factor of the areas. So here's another concept that relies on the idea that a cross section is a slice that's parallel to the base of a cone or a prism or a pyramid. If two general cones have the same base area and the same height, then any cross sections at the same distance away from the vertex are going to have the same area, regardless of what the shape looks like. Again, because if area is not dependent on shape, so it really doesn't matter what the shape is. If they have the same area and they have the same height, so they have the same distance away from the center of dilation, then at every level, the corresponding cross sections are going to have the same area. So here's an example of that. We have a circular cone and a general pyramid. The bases of the cones are equal in area and the heights are the same. So we're going to sketch a slice in each of them that is parallel to the base and 1/3 the distance from the vertex than the base plane, which means it's going to be closer. So if I can sketch this, he's going to be here. He's going to be at the same height. If this distance is 1, then the overall distance will be 3. That's the ratio, 1 to 3. That's why it's 1/3 of the way. If the area of the base of the circular cone is 616, and we said that the bases are equal in area, that means the area of the pyramid is also 616. We want to find the area of this slice here. And again, it's just using the scale factor. So I'm going from big to little. That means my scale factor needs to be 1 over 3. And it's always related back to the vertex. So it's 1 unit away from the vertex and the base is 3 units away from the vertex. If I'm going to square that to get the area, it's going to be 1 over 3 squared, and that ends up being 1 over 9. To find the area of the small slice, you take the 6/16 and you multiply it by 1/9, because again we're making it smaller because this slice is clearly much smaller than the big slice down there. And you finish with that and you end up with an area of 68.4 square units. So if this slice is 68.4 square units, what's this slice going to be? And I'll let you think about that, and we will talk more about this in class.